I'm Tom Soja.
I'm Jacob Martin.
I'm Yash, and this is our Design Phase 3 presentation for our physics demonstration model. So brief overview, we're only going to be covering the main stuff from Design Phase 3 simply because of time constraints. We're going to review some of the stuff from the project management exercise, see what worked, what didn't work. We're going to go through a 3D CAD model that we created for our PDM project, and go over the concept selection process again. We're going to talk about product architecture, industrial design, and assembly times, and then how we use that assembly time to come up with cost figures. And then we're going to talk a little bit about what could have been changed and future goals for the project, and move on from there. Right, so a Gantt chart update. You'll see here that luckily we managed to finish all the stuff that we wanted to finish on time. All these progress bars are at 100% and all the boxes are checked. If we had to change something, we would change the fact that we had these sequential tasks here with IP search, concept generation, and concept testing. While doing it, we realized that it might have been better if we had them one coupled and two parallel. In that case, we could have a lot more iterations and have a better design. We also wish that we had done more prototyping. We do feel we had enough time for prototyping. We just wanted to have more iterations to go through, maybe 2 or 3, as opposed to the maybe 1.5 that we actually ended up with. Again, this is our DSM. You'll see that everything has been darkened, representing that all flows have been completed. Again, this was the only cover task that we had, industrial design and design for manufacture, and we would have wanted, in hindsight, to have IP search, concept generation, and concept testing sort of all coupled so that we could have had more iterations and, like I said, made our design better.
So now we're going to talk about the concept generation and selection process that we went through towards the end of DP2. And so this is our table screening, our concept screening table, and we use that to eliminate the collision screw and ramp solution to making sure that all of our solutions were being graded based on the criteria we wanted. And so from there we went on to make a concept scoring table, which is right here. And our main selection criteria were setup time, runtime, aesthetics, repeatability, customizability, and size. And so from those criteria and weights that we gave those criteria, ultimately the tube, Ferris wheel, and funnel solution came out as the best solution based on those criteria. So now we're going to go into the 3D model for that solution and how it's set up for the final product. And so from the front view, we have the tunnel that enters the ball, like where the ball enters into where the Ferris wheel picks up the ball in more of like a claw arm, and that will rotate based on the Arduino right over here. And then on the back side, when the ball gets up top, it will drop into the funnel and go down into the exit, which here you can see that the orthographic views of the final product and some of the dimensions that go along with it. So now we're going to talk about the product architecture, where we took the different functions of the product and clumped them together to determine what parts of the product were for different functions. And so those products, well, those functions were like receiving the ball and like releasing the ball, and this table, this figure shows where those functions are and what part of the product does those functions. As you can see, most of the functions are modular, and that was one of the main focuses of our product, so that we can eventually swap out different sections. So like receiving the ball, we can do a different entrance than a tunnel. For example, a collision or another type of interaction, and we can sell those as just different variants of the product as a big platform.
Now we're going to talk about the industrial design quality of our product, and as you can see here, basically ergonomics, the ease of use was very high because it's very easy to use. All you need to do is basically put the ball in and it runs, and then the ease of maintenance is not very easy because all the parts are injection molded, so if something breaks, you need to buy a new part, you can't fix it yourself. For the quantity of user interaction, it's pretty low because it pretty much does one thing with currently only one set of exit, giving energy, and entrance. You can't switch anything out, so there's not a lot of quantity when it comes to setting up the product. Quality is very high because it does exactly what it's supposed to, and it works great. The novelty of the user interaction is also very cool because it combines Arduino, so it's sort of like a new thing, not really seen on the market before. The safety is obviously very high. I mean, it's for high school kids, so we made sure that it was 100% safe. And in terms of the aesthetics, the product differentiation and pride of ownership is high, but not all the way, because BRGs are on the market. This is not necessarily a new thing. The only thing that's new is combining Arduino with it. And in terms of the assembly time, using the charts in the book, we determined that the total assembly time is 143.88 seconds, which is 2.9 minutes. And this is also going off the assumption that we have injection molded parts, which we currently don't have. And this reduces the assembly time of what it actually took to make our prototype. And basically wiring the Arduino and assembling the Ferris wheel took the most setup time, and that was due to the amount of wires that we needed to use, as well as the fact that we needed to put together the Ferris wheel rather than just have it completely injection molded.
And so based on those terms, we came up with a cost sheet to figure out our production costs for this product. The thing to note here is we listed out our components, like he said, assuming that they were all going to be injection molded. We figured out how much they weighed, and then based on the price of plastic, which we assumed to be $20 per kilogram, we came out with a procurement cost, and then we used the assembly labor times to come up with an assembly cost, and all of that combined per unit came down to $33.98. Assuming that we produce 1,000 units as we had planned to initially, that total annual cost came up to $37.5 thousand dollars. Again, we had assumed that we would have an annual cost of $42,000 or so and above, and so that seems like a good cost. There's also the overhead cost of $3,500, and that comes from the fact that these molds that are listed here with that cost have to be replaced every year, and that's the assumption that we're making. Of course, all of this is for a steady state production process, so this doesn't account for changes in design, for improvements in safety, and anything that's unscheduled and comes out of plan. So having gone through all of this, a few things that we would have wanted to change. Definitely wanted more time in prototyping. We ended up maybe creating one model that sort of worked, didn't work. There was one component that gave us a lot of trouble, and then we tried to improve that. And we had a lot of prototyping for that, but not for anything else. And I think it would have been easier and would have been a lot more fun if we had more time to just spend prototyping the product. Obviously, we couldn't do that because we have other classes that we needed to attend to. It would have also been a lot more fun if we could actually go into the core engineering design. We realized the importance of this class, and it was a great time actually learning about the project management and different parts of product planning and development. But it was important, or it might have been more fun for maybe a larger scale project to actually do engineering analysis, maybe go through the dynamical models and failure modes and failure structures and stress analysis, stuff like that. And then obviously we, in an ideal world, would be increasing the modularity of the design. So a lot of the product architecture that Jacob spoke about, we would be improving on that so that if we have a whole line of products that we're selling, you can sort of pick and choose from them, put them together, take them apart, increase customer interaction, because right now we only have the Arduino, and sort of change on that. I do believe that a lot of that would have been fixed if we had coupled our tasks with IP search, concept testing, and concept generation, like we mentioned earlier. which would have made the product more user-friendly and a lot better planned.
In conclusion, basically what happened is we were able to finish on time. We wish we had more time for prototyping, but we did get the product finished. The final product will be injection molded. That was what our assembly time and cost is based off of. The availability of buying optional subsystems to change some of the features is what our hope is for the system, so that for the future, so that we can increase the quantity of user interaction and customization. And we would like to. We also had a high emphasis on high quality customer interaction and product differentiation, which is what our goal for the future is. The assembly takes just under 3 minutes, which is actually pretty quick, and the only reason it took more than about 1 minute was because of the Arduino wiring, which takes a lot of time because they're very small and there's a lot of them. And next time we would like to allow more time for prototyping, for iterations with better failure analysis, so that we can make a prototype model that is completely functional and gives us a better idea of how our product performs. I'm Thomas Soja.
I'm Jacob Martin.
My name's Josh.
Uh,
Alright, let's start over. Because I also